Okay, good afternoon, everybody. Kids, somebody jump off mute and give me a sound check. Can you guys hear me okay?
We can hear you. Yep.
I can hear you guys. First time. Awesome. Thanks, guys. All right. Welcome back to Monday. So today we're going to start on our slide deck 2. This is our week 2 topics, moving into thermodynamics, kinetics, and then on to other components. So we're going to be starting with our intro thermo section. So as a reminder, we've completed our acid-base chemistry review, including our calculations. On Friday, we went through one example of a buffer type calculation in class. I've now posted a full pencast walking through sort of the basic acid-base problem sets online, so please go review that one. Those types of sort of work problems, there's 2 wins. So there's what I have sort of walked through the logic of it. Also, if you try them, these are on the acid-base assessment. There are fully sort of all work problems as a PDF online as well. So use those as a resource to sort of test out how you're doing. And again, main thing to do is to start doing the acid-base problem set and assignments right now, and the assessment. Remember, that's the one you can do infinite time and infinite attempts. So moving on now. We're going to start into the area of thermodynamics. So this squarely is what we call physical chemistry. By definition, physical chemistry is really about measuring things. It's about measuring properties and focusing on quantification of the world around us. Broadly speaking, physical chemistry have these sort of disciplines. So thermo, kinetics, quantum, and statistical. So quick thing in chat and otherwise. Who's heard of thermodynamics before? Some point, yeah. What about kinetics? Again, topics, yes, no, you've heard of it. Sure. Quantum, does anybody heard of it besides sort of like the, Stephen Hawking and kind of awesome points a little bit? And then statistical mechanics, anybody else sort of touched that one? Yeah, that's a little bit lighter. Broadly speaking, we're all talking about different ways or different scales to look at the world. Kinetics is functionally looking at change over time. That's in the name. Kinetics is talking about something with a stopwatch, looking at differences with time. Thermodynamics is in the name. Thermodynamics, anybody have an idea of what we're trying to talk about in terms of what we're studying? If you look at those 2 words, thermo and dymo, yeah. Temperature, thermo, it's actually heat. That's right. Thermo is talking about the heat. Dynamics, what is dynamics usually talking about? Yeah, change, exactly. Thermodynamics functionally is looking at how heat or energy moves around in a system. So it's talking about redistributions of energy, and then really that's in its name, that was where it sort of came from. It's looking at how heat, as our major unit of energy for all things chemistry and all things sort of in the physical world, how heat redistributes in systems. So this is about doing reactions or doing processes. These can be physical things too, that create these changes in energy or moving around. So the most important thing to keep in your head is it's always about changing, moving these things, and usually we're talking about moving packages of energy, which we're going to define as heat. It's heat moving around between different parts, and heat can be stored, heat can be turned into, can be used as sort of a force to either create bonds, or we can break bonds to release heat too. So that's where it sort of intersects with a lot of the reaction stuff we're talking about. Quantum, we will not be talking about deeply in this course. That's more about how individual particles sort of behave. Statistical mechanics is more about sort of the engineering side of probabilities. When we're dealing with these systems that are really hard to explain, right, these small molecules, what we have to do is look at the average behavior of them. And we talk a little bit about some of that, but functionally, we're really going to focus on the first 2 with this emphasis on thermo first. So right there in the name, thermodynamics, it's the study of bulk properties. So this is about large areas of matter and how they interact with heat. Now in general, like we've talked about this in physics probably, energy can be thought of usually in these kind of buckets: potential energy, kinetic energy, and chemical energy. Potential energy, and if you've looked at sort of like any type of, we will look at reaction mechanisms a little bit. That's towards the end of the kinetic section. But if you remember in physics, looking at just general kinematics, right, movements of objects, you're used to looking at something like this diagram of a pendulum or somebody swinging, right? This is a case where we can convert between kinetic energy and potential energy. At the very top of the arc, all of the energy in that swing is contained as potential energy. The person is not moving when we're at that very top piece, but it has a lot of potential to convert back into kinetic energy. As it drops down the very bottom of the swing, you're moving as fast as possible. All of your energy is now in kinetic energy. So the reason we bring this up is that you guys should be sort of generally familiar with this concept that energy can move between buckets. Like we could have a system like this swinging person, and the energy contained can shift between how it's being stored, either potential or kinetic. Same kind of thing happens in molecules. The only difference really is how we store energy, and it can have things like potential. Here, potential energy is defined as a weight of an object against gravity pulling it down. Potential energy can be stored in the form of chemical bonds. So this is where if we take energy and we try to keep it for later, for releasing at a later time, we can form bonds, which are these connections or sharing of electrons between two different atoms. And those bonds have different energy quantities. They have different energy values depending on what the bond is and what part of the molecule they're contained in. So this can be really useful. This is a way of keeping energy as fuel for doing something later on. It's a way of storing it up. So in a mind, think of chemical bonds as kind of like this chemical version of potential energy. It's ready to go for later time, right? So heat can be brought in. We use that heat to do a reaction to drive a process that we form this bond. And that bond is a way of holding on to the energy that we then want to release at some later time. So how do we study things? And again, this is a big process where the biggest problem when we're talking about any of these things is we're talking a lot about abstract quantities, either things that are on the scale of the universe all the way down to atoms that are very difficult to resolve. They're not something that you see or interact with on a day-to-day basis. So this is where these models come in. We need to ways of sort of defining them or putting them in a context for us to understand. So anything in the universe can sort of be brought down to these basic properties. What we have to do is start by saying there is something we're going to decide to look at. And I said it before when we talked about that person swinging. If I'm trying to understand how energy moves around when somebody is on this swing, you need to start with a framework to say the thing I am going to study is that person and that swing. It has to contain enough parts to explain the behavior you're trying to understand. And we call that the system. So, just as far as definition goes, when we're talking about things that we are the unit or thing that is under study, we call it the thermodynamic system. And it's just, this can be anything. It can be a single chemical reaction. It could be a bunch of water where we're putting a hot rock into it. Whatever we're trying to understand in that concept of moving around energy, we define as the piece that we are studying is this system. What that means is the divider between the thing we're studying and everything outside that thing, the rest of the universe, we call the boundary. The boundary is this object. It can be imaginary, it could be a physical sort of container, but it's a limit that we say, look, we're just defining it that inside this boundary is the thing we're studying, outside this boundary is the thing that we are not. The boundary is just the point at which it crosses between the two, and it can be a conceptual thing where we may not have a hard line. This is partly a decision when you're actually looking about setting up the experiment that we may have to decide. What that means is everything outside that system is what we call the surroundings. So by doing this, what we've now done is defined where something is that we're studying, the system, and where something is outside the system, the surroundings. The boundary is the divider between the two. What we now have is where energy is and where it may be going to. Things can enter the system from the surroundings. Things can leave the system to the surroundings. So the transition we're really talking about is crossing this boundary. Overall, everything, the surroundings, boundary, system, we call that the universe. That is all the bits and pieces. So that's the sum of all different pieces. Now we need these four concepts, right? System, surroundings, boundary, and universe, because it allows us to make some simple definitions. So for example, all the mass in the universe. What do you guys know about, what's an assumption we could make about all the mass in the universe? Constant, not constant, changing, massively big. Yeah, like we can talk on astronomical scales. There's the interconversion between mass and energy, but we start off, yeah, a lot of it, dark energy, dark matter. But this concept of saying, look, there's the total, which in the total, we're going to make a lot of assumptions like total energy in what we call this universe may be constant. Total mass may be constant. So that's important because now we have this total quantity. Having system and surroundings are different locations. We can say mass could start off in the system and move to the surroundings. So we have a differential, but the total remains constant. If it's lost somewhere, it's going to show up somewhere else. That's important because sometimes we can measure one of these three quantities, either total amount of energy inside the system, or total amount of energy in the surroundings, or total all over. Sometimes we only get two of these measurements, but because of these kinds of relationships, measuring two gets us that last one. So by inference, we'll be doing a lot of things like this. It also means that the boundary, that's the cut between leaving the system and out to the surroundings. Okay, so conceptually, this is just about laying the sort of playground that we're going to be working with. So the boundary is important because this is the point of transition. This is where we're saying if it leaves the system, it must cross the boundary in order to get outside the system. And this could be energy or matter. Either of those two things can move. In the context of thermodynamics, it could be either of these parts, but we'll make a couple of simplifying sort of assumptions. But the important part is the boundary's job is to define where it leaves the point of interest, the system, and where it goes into the surroundings, or vice versa, enters the system from the surroundings. So it's important to have what we call a clearly defined boundary, right? And it has to not change depending how the reaction is going. It's about, we will use a variety of different assumptions as we move through this in order to again, make our measurements possible. But this is a kind of a way I want you to always come back and think about it. As we introduce all the different concepts like the first law, the second law, the third law of thermodynamics, I always sort of map it back over this general concept and then understand, well, why did we choose those assumptions in order to make these kinds of measurements, or how do they hold or not? There's definitely some things that are really complicated where some of our simple assumptions do not hold, and that's this topic of much more complicated sort of studies. The whole field of quantum mechanics exists because some of our assumptions about how simple heat and mass move do not apply when the system becomes the atom, for example. So sometimes by choosing a certain system and applying our idea, we see that our theory breaks down and we need a new theory to explain it. Yes, we're going to get to that point. The open-closed type systems, different kinds of systems matter. All right, if you imagine this, here's our picture of the universe. We have the Earth. As an example, let's say we wanted to measure a property about the Earth. And specifically, let's say we're going to measure the total amount of energy on Earth. What would I call my system? Where's my boundary? What am I defining as my surroundings? If I just have to do that kind of a study. I'm trying to make an estimate for the total amount of energy on Earth. What would be my system there, first of all? Okay, Earth is the system. Okay, some people have made the defining boundary as the atmosphere, okay? And then outside of that is going to be my surroundings, right? That's going to be everything else. So, but again, let's be a little finer point on that. The universe is too massive. If I actually wanted to make a quantity measurement, if I said the surroundings was everything, that makes it really hard to figure out like what our total amount of energy bubble is. So why not, instead of saying the universe, I'm just going to localize it to the solar system as an approximation to the surroundings. We have to do that sometimes. We have to say that, yeah, you're right. The accurate and most perfect answer to everything outside the Earth is the universe. But without a tangible end to that, the measurement becomes impossible. We all go home, nothing we can do. Sometimes we need to make a definitive sort of a cut, an approximation, which allows us to still make a useful measurement to make a useful prediction. That's the concept of most of science, right? We have to sometimes say, look, I think I don't know anything about the Earth, but I'm going to choose that the Earth is basically like a basketball. It's a big round object. I do know something about a basketball. I will try to apply those sort of concepts. But yeah, you're not wrong either. What you define as system or surroundings, there really is no dead right answer. And this is something you have to consider when you read data about stuff like climate change, how a vaccine is working. All these individual studies had to make careful decisions about what they're saying my system is, my surroundings, my control, and your actual answers will change quite specifically as those sort of assumptions are being made, okay? But yeah, there's nothing that's definitely wrong about this. So, but what we can do to help simplify is to break down the systems into a couple different categories. We have what are called open systems, closed systems, and isolated systems. And we have a specific definition between each of these three. The open system is the most complicated. We're saying that in an open system, both energy and matter can cross the boundary. So that would be something like, a cup, an open cup system like this, where this is my system, my room here, my office becomes the surroundings. The boundary being sort of this dotted, physical line is the cup. I don't really have a dead physical line here on top, right? I'm just going to say it's this kind of a geographic here. It's open on top here. So that becomes my system. I become my boundary, but matter, things can evaporate or condense, and energy can move between it. So if you think of this in terms of one of my favorite beverages, coffee, a coffee cup would be considered to be an open system. We can have steam lose out of it, or if it cools down, we could potentially condense steam into it. Heat can definitely move in and out. The cup can be hot. It's different where that heat moves out the top versus out the side. But these are complicated, right? If we have to make measurements about this, we have to keep track of all of those individual things. We almost need like a customs agent around that boundary to watch where did all the matter and energy go. So very accurate, hard to measure. A closed system really simplifies our life. The closed system, we're going to make a definition where you're like, you know what? I am going to allow energy to move, but I'm going to make the assumption that matter does not move, right? So in this case, energy can move freely, but what happens is matter, the mass inside the system, remains constant. It's closed so that matter cannot transfer, but energy does. So an example might be like you guys were saying, the Earth. And that's still a little bit of an approximation. We're saying that matter does not leave the Earth, but heat can leave and energy can come in by way of the sun or the universe. We can also irradiate energy back out from this one. So closed systems are easier because we can keep track of all the mass that have to be in here. We just have to watch energy moving around. The last one, super easy, are isolated systems. These are things where neither heat or energy and matter cannot cross the boundary. They're completely cut off from their surroundings. These are really easy to describe inside because we're not losing anything. We have complete mass and energy balance where all the energy inside this isolated system stays inside there and all of the matter stays inside there. So a pressure cooker is a good example. When it's when you're actually using it, assume it's not plugged in. Imagine it's already heated. There's no heat exchange with the rest of the system, and there's no matter exchange. Now, obviously, we can change that. We can open the pressure cooker, but as soon as we open the lid, we've created an open system. We've opened it up, so now the boundary is permeable. Can anybody give me another example of an isolated system? In the context of coffee, what would be another isolated system you guys might have? Yeah, a thermos is a great example, right? It's something where the heat can't change. It's closed so that there's no evaporation. Fridge, sure, maybe a sealed system like this that's holding at temperature. Now, remember, one of the things I want to put an emphasis on too, all of the things we're talking about, like we could absolutely poke holes in each of those sorts of analogies. Oh, a thermos isn't perfectly isolated. It still leaks heat. My coffee eventually gets cold, right? Okay, if I open up that thermos to drink it, well, now I don't have an isolated system again. All of these descriptions of different kinds of setups are meant to help think about what is constant, what can I measure, and how do I get information or isolation or an answer between different things. But they're constructs. These are ways of setting up for experiments to allow us to do certain measurements. So that's the first. We have these three kinds, right? The systems are either going to be open, hard to measure, very realistic, closed, easier to measure, also more realistic. A lot of our systems are going to be these closed systems. Isolated, which are these completely mass and energy balanced inside the system. Downside with an isolated system is it's completely isolated. We don't get to see a lot about this exchange, right? Energy leaving the system is all about studying what's happening inside the system. If it's isolated, nothing's happening from the perspective of the surroundings. It's a black box to us. This would be like a black box or like a black hole, for example. It's hard to study a black hole because no information comes back out of it either. So, to talk about measurements or properties of a system, we have what are called the state. The state is anything that we can describe or measure to talk about about what's inside the system or a property of the system. It's anything that has a measurable quantity, right? So these are anything to help describe, if we had to sort of tell somebody about what this system is, we have to give them enough detail so that they could go and reproduce this in their lab themselves. So again, if this is my open system, I need to describe things about this system so somebody else could potentially set this system up and study it themselves. So as an example, what do you guys think you'd need to know about this so that you could have an identical thing so we could both be studying the same object? What are things I might have to measure or tell you about this? Volume, that's a good part, right? What else? Okay, yeah, mass of the jar, temperature inside here, concentration, yeah, thickness of the glass. Does anyone want to know what that is? Yeah, type of liquid. This could be vodka, this could be clear soda, right? Everything is really, really, really different. So you need to know about these sorts of things. We call them usually chemical properties. In the context of thermodynamics, because it goes beyond just the simple chemistry, it's measurements about things like temperature, how things are described right now at this instant, we bin them all together as state variables. So generally, the state of a system is something that describes the system we're studying. The state variable is something we can describe, but does not matter how that system was achieved. In other words, what I mean is, this jar here has a volume. It doesn't matter if I poured it out of a much larger jar or a much larger beaker. It doesn't matter if I took and filled this in 10 different steps. The volume it has is just the volume it has right now. It doesn't matter if to achieve this volume, I could either fill it up all in one shot or I could fill it in many small shots. The value that matters is how much is in here. So the concept of a state variable, what makes them special is we call them path independent. It is just a description of this object. You don't need to know how I achieved that object as long as you have the same numbers, mass, size of the jar, temperature in the room. That will be, we're both talking about the same kind of a state, the same kind of a system. So that's the important thing. They're descriptors, but it doesn't matter how you arrived at that. It just has to be the same. We both have to agree that those values line up. So examples are temperature, volume, pressure, mass, density, concentration, all those different pieces, right? So within the concept, so we have this hierarchy building up. 1, we have system and surroundings. 2, we have systems that are either open, closed, or isolated. 3, systems can be described by what we call state variables, right? These are just descriptors about this object or this system we're studying. Last, state variables have 2 different flavors. We call them intensive or extensive. So an intensive variable is independent of its size. So that's the mnemonic you should use. An intensive variable is independent of the size of the system. So for an example, this is mystery liquid, right? What is a property in here of this liquid that doesn't matter how big that system is? Yeah, the temperature, right? If I have, let's say this is 100 milliliters of this liquid at 50 degrees, I could have 1,000 milliliters at 50 degrees. I could have 1 milliliter at 50 degrees. A temperature is not necessarily dependent on the size. Things like heat capacity is another good example, a descriptor of how much energy is needed to change this. What else? Well, concentration, yeah, exactly. This system here wouldn't matter. Density, concentration, the concentration of the solution won't change if I've got a little bit or a lot. What about weight? Mass. More will weigh more, right? That is an extensive variable. Things that change depending on size are called extensive variables. So the visual example we here have on the screen, let's say we've got a small rock and a big rock. The mass of those two absolutely is an extensive variable. The density of that rock will not change because density, what are the units of density? Think about that for just a second. Units of density, yeah, grams per volume, right? What about concentration? What's the units of concentration? Moles per liter. It's not mole. Yeah, mole per liter, capital M molar. So what you'll notice is a lot of intensive variables have what we call these ratio properties. It's a value that has been normalized by some other variable, or a ratio of two extensive variables generally will create an intensive variable. Mass is extensive, bigger and smaller. Volume is extensive. But if we take mass per volume, density, that is now intensive. Because what we're doing is we're saying that the weight per some amount of volume actually has this ratioed property, which is now intensive. It doesn't depend on the size of the system because it's ratioed against the size of the system. This is another common thing that you'll see to help you sort between these two. Any questions about that general concept, intensive versus extensive? We're going to try a couple different ones to see what you guys think. Yeah, Carmen.
Sorry, I have a question.
Yeah.
So pretty much if we put two extensive variables together, it becomes an intensive variable?
As a ratio. If you divide, like for example, density is a good way to think about it. Mass, grams, is extensive. Volume, liters, is extensive. But if we take the ratio, grams per volume, that becomes an intensive variable because what we're saying is the same weight per volume will be true for all of that thing. Again, this rock here, big or small, has the same concentration of minerals because we're just looking at different overall sizes, but the ratio of weight over volume would be the same.
Okay, thank you.
No problem. All right, let's try a couple different examples. All right, we have a beaker with a little bit of liquid, a beaker with a lot of liquid. Would temperature for these two different systems be the same? Another way to think about it, are they intensive or extensive? Yeah, absolutely. This is an intensive variable because temperature of, let's say, the water in both of these two beakers would be independent of how much is there. They may be 5 mils versus 100 mils, but they're all at the same temperature. They have the same value, right? So yes.
So
yep, please.
if the temperature was changing, so if you combined temperature with time, then it would be different. It would be extensive.
Yeah, so there's two things there. First of all, you just mentioned if I was going to be changing the temperature, that's where we're heating it up, right? That's not a state variable anymore. That is what we call a path variable. You're talking about how does something like temperature change, not what is the temperature right now. Does that make sense, that the difference between the two?
Yes.
So the differential, and you're right, this is where it kind of feels weird because you're like, well, but if I have a little bit of water, it will get hotter faster. That's true. But that's talking about how we change it, not if I had to describe a pot of boiling water, it doesn't matter how big that pot of boiling water is, they will both be boiling at 100 degrees C, assuming pressure, yada yada. It doesn't matter a little bit of water or a lot of water, the boiling point of water will be 100, right? The temperature at which they boil will be the same. You're right though, changes are different, and we'll talk about those after. How we affect change will have a property of size associated with it. Edward.
So if the volume of the water is the same, but the temperature is different, then would temperature be an extensive variable?
No, those would just be two different systems, right? We have they're still intensive state variables. If I told you, think of it this way. This is kind of like if you read out a script for a lab, Do you need to know something about its volume to just have at your benchtop? If I tell you, make a beaker of water at 10 degrees, hard stop. You could choose to do 1 mil, 10 mils, 100 mils. You just need water, 10 degrees. That's all that matters. You don't care how much there is. If that's your mission is water at 10 degrees, you choose how much you want.
Okay, that makes sense.
Make sense? So yeah, heating up quicker, all those other points, those are about change over time. And those do matter, right? Those size and scale will matter. But properties are what we're talking about now. Descriptors of a system as it sort of stands. Okay, let's try one more. What about mass? If they had these two guys. If we have these two guys here, is this intensive or extensive? Do I need to know how much there is in order to show these? Yeah, absolutely. The mass will be extensive. The weight of the water matters. You need to know this value in order for you to recapitulate these two different states. So this is an extensive variable for sure. Density. If I asked you for the density of water in a little beaker versus a big beaker, intensive or extensive? Yeah, intensive, right? This water, same water here, same water there, they all have the same density. It's a property of it. It doesn't matter how much there is. And also look at the units too. This is what we were talking before. The value for density is equal to mass over volume. These ratios are another quick clue. If you look at the units, it's another clue to say, am I dealing with intensive or extensive variables? So yes, it's intensive. All right, so take a quick second. Sort these out. Which of these, if you go down this list, would be intensive versus extensive? So we're going to go down one by one. I want you guys to just kind of keep track of them, maybe even discuss it out, and we'll split them out after. So volume we've discussed. Survey says what? In the chat, volume would be intensive or extensive. Okay, getting a lot of extensive there. Good. Pressure. Intensive or extensive? Half mix. Got a little bit of in and X. Yep. Mass. Okay. That one is a pretty clear extensive, I think. Temperature. Yeah, we talked this one. You guys remember temperature? I think definitely is in the context of intensive. Density. Yeah, definitely. I think density is intensive. We talked through it. Number of moles. So the physical quantity mole. That looks like an extensive vote. Molar mass. What are the units of molar mass? Yeah, grams per mole, right? Concentration. Yeah, intensive, I think. What about energy? All right, that one, that's a good point of discussion. All right, good. So I think generally, this is how I would split them up. Volume, mass, number of moles are extensive variables for sure. Intensive variables, pressure, temperature, density, molar mass, concentration. Energy binning in the extensive category. Now, okay, does any of these jump out as like, whoa, 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 that is on a side of the division that I totally disagree with, objection, Your Honor. Let me hear you now. What do you guys got? What's something that jumps out as like, why is that on that side? Yeah, pressure is usually one. What about, what else? Yeah, Sam.
Oh yeah, no, it's just pressure, yeah.
Just pressure?
Yeah.
Energy might be the other one that might sort of bump people up. Okay, let's talk pressure. What are the units of pressure? Yeah, force over area, right? Pressure per square inch, or something to that effect, right? All units of pressure have this energy over area. So it makes sense, right? Newton meter squared is another good one too. That is, again, it means it's normalizing based on the size. The pressure, right now, my hand, so by context, this is real, this isn't a Zoom background, right? This is a door, thank you. You can see by height, I'm about the same height as the average door. So I'm probably a larger system than a lot of you guys. My hand is bigger than a lot of you guys. Would you say the atmospheric pressure being exerted on my hand, if we're all here in Vancouver, is the same? Right? The size doesn't matter. The system being bigger, the pressure on my skin is the same because it's averaged over the size of it, right? It's force over area. We're dividing by a unit value of area, which then normalizes the point. Physical pressure, maybe the force I experience would be different, but pressure is because it's force over area, this ratio of two extensive variables, it becomes intensive again.
I'm sorry, I don't really understand what you mean. Like, you're saying the pressure would change, but then it wouldn't change. So, like...
No. What I'm saying is, if I were to measure the pressure that the system, am experiencing because of the atmosphere, right? The pressure I am experiencing here, the pressure which I call atmospheric pressure, is identical to you or anything else, no matter what the size is. The force being exerted on an object in the atmosphere is identical no matter how big that object is.
Oh, okay. So
right?
Like you're talking about like the object size changing, not the system.
Yes. Well, but object being the system, right? Like the physical force, if I were to count up how many newtons I am experiencing, I would have to know my entire surface area to measure that. That's not pressure. That's just force from the atmosphere. Pressure is force over area. Since it's force over area, doesn't matter how big the object is, they are all experiencing the same force over area. We divide by...
I meant like surroundings, not system.
Yeah, exactly. Yep. So that's, again, the way you look at it is look at your ratio. The ratio should help you that point out. Energy, extensive. Now, what would the units have to be for energy to definitely put it in the extensive category? Joules, yeah. Kelvin, right? Something that is a measure of energy content. So, like, does anybody know what the units for temperature usually are? Like, yeah, deltas, like degrees, right? Kelvin. But it's energy, it's an average amount of kinetic energy in a certain space. It has a ratio value. This is the one thing that makes it kind of tricky sometimes is some of the units that we're used to seeing do not have this ratio type quantity, but remember, if you go down to the primary definitions, there will be somewhere. Temperature really is average kinetic energy of a particle in a system. So it has this averaging value. Energy could be how much energy is in this water at this temperature. More water will have more energy because there's just more of it. If you think of energy or define energy as simply kilojoules. What if I wasn't saying energy, but molar enthalpy, for example? Does anybody know what a molar enthalpy value is? That would be no. Yeah, delta H, yeah, it's usually that. But remember, molar enthalpy, if I say the word something like molar enthalpy, what does it start to sound like I'm doing? Look back to the other ones we talked here. Number of moles versus molar mass. What's the difference between those two? Yeah, number of moles is just moles. Molar mass is moles per gram. It becomes a ratio. Energy is just how much energy, joules, is in a system. But if I said molar energy, like number of energy per reaction or per number of moles, as soon as I've got that ratio value, it becomes an intensive property again. You can have energy defined, but usually, again, it's not just energy of a system. It will be molar enthalpy quantities, molar entropy, Gibbs free energy in a molar value. Those will be defined as an intensive value again. But again, they're always divided by a certain number of mass. So looking at the units will definitely, yeah, joules per mole would make this thing into an intensive value. Exactly. Okay, we're going to practice this as we go through. Now, the next piece too is we have to define the types of systems we're going to study. We said there's open, closed, isolated. We've got state variables. State variables talk about a measured quantity, not about how we arrived at it, but just a value I can measure about this object right now. The other important thing we're going to talk about are what I call this concept of equilibrium. We've already discussed this before. So in the concept of acids and bases, how do I define the equilibrium position? If I had to say, you got to make a call for is this solution at equilibrium? What is something you could define? If you had to teach somebody about why you are saying, yes, this is at equilibrium. I'm basing my stable. Okay, what else? No change in pH. Forward equilibrium equals the back equilibrium. Yep. K equals Q. Those are all good examples. Exactly. What you're really getting at here, right, is that there's no net change over time. Unless I add energy, I add mass, I have to bump the system somehow for something else to happen. What we're saying is the state does not matter based on how much time I wait, right? So, back to my glass of water. This water has a temperature. Is it at equilibrium? Well, I could put a temperature probe in here, check the temperature, wait some period of time, check it again. If the temperature is not changing over periods of time, I can say it is at equilibrium. That means that the state variable that I'm looking at does not depend on how long I wait. It is not an instantaneous value, it is an equilibrium value. So this is a concept that really matters. For thermodynamics, we are always studying systems at equilibrium. We are going to then do something to the system. We will change it. We will add energy. We will add mass. And then we wait for it to reach equilibrium again. The calculations and most of the assumptions we're going to apply, all the rules and laws that I'm going to be talking about in the concept of thermodynamics, the most important thing to remember, we're talking about systems that start at equilibrium. The laws apply to that condition. We're going to do a change. The change matters. There's math that happens there. That's the path. And then we have a final state that is going to be equilibrium again. So we start where there's no net change. We do something. That's the cool part of it. And then we wait until there's no more change again. We move from equilibrium position to equilibrium position. Why this matters is a lot of the things we were just discussing that seem kind of out of place. Well, what if I heat something up? Won't it change temperature faster? Yes, those are changes. But the properties we're discussing in terms of thermodynamics are talking about I start at an equilibrium state and I finish at an equilibrium state. And we measure the differences between the two. The path gets a little bit more complicated. We will talk about that. But we define them as this part. So always remember, these equilibrium things matter because we have really, really good math and laws that we can apply to calculate things about that. So who's seen this amazing equation before? PV equals nRT. Ideal gas law, right? So the ideal gas law, you guys should be familiar with it in terms of the terms. P is the pressure, V, the volume of the gas, N, number of moles, R is the universal gas constant, and T always will be in temperature, right? It's the absolute or instantaneous temperature here. One thing to note, number one thing people will mess up. R, who knows what the value for R is? If I had to go right now and look it up, does anybody know? This is where you get to show let your nerd flag fly. What is the value of R? Okay, depend. Remember, it's the universal gas constant. So constant really sounds important, right? 8.314 is 1, and then the other one I see is 0.82 something something. Yes, you are both correct, but look at the units. So 8.314 is the correct value for R when you're dealing with units of joules per mole. The 0.82 is the correct value when you're dealing with, is it kilopascals? I always have to go look this up too. The fact is, yes, it is a constant. It does not change. But depending on the units that you are applying, and it always is the units of energy that you are dealing with, the R value may be different. So use the right one in the right place. Where you get that and how you change between the two comes down to some of the units you're going to be using. Use your dimensional analysis between if you're given values of energy in joules per mole, or if you're given the values of energy in kilopascals or Newton meter squared. Those energy values will give you different values of R you have to compare against. So this is, I flag it right now. We will practice this part later, but this is the number one thing that messes people up is how do you use the right value for R? There is only one or two. Look at your dimensional unit analysis to select between them. Okay, but most importantly, back to the concept of equilibrium. The universal gas law, the ideal gas law applies. It's a great way. This is awesome because we can just know a couple pieces of information and I can fill in the rest. R is a constant. which means I only need 4 properties of any gas: the pressure, the volume, the number of moles, and the temperature. Just as a quick thing, this is one of those things that kind of, again, once you've done this a while, it blows your mind. Does anything about this universal gas law tell you about what gas you're talking about? No. Doesn't matter if this is helium, it doesn't matter if it's methane, doesn't matter if it's oxygen. If it is an ideal gas, this law applies, which means we can study something about one type of gas and imply the details of another type of gas. It's really important because it has this sort of transitive property. It has predictive value. It is a law. That's why we sort of talk about it in this way. The most important thing, though, is it only applies to ideal gases at equilibrium. So again, it needs to be a system that is not changing temperature. It's not changing pressure. We can know something about that change, but the ideal gas law talks about a state in which the whole system is at its equilibrium position. To be an ideal gas mentally, and again, this is where we don't care what type of gas it is, if it's hydrogen, helium, whatever, there's a couple of things it has to make, and again, for the context of everything we will talk about here, we're going to assume all gases obey the universal gas law. But for your reference, does anybody know what those things are, what they have to be in order to qualify as a universal gas law? Or an ideal gas, excuse me. Right? No loss in energy from collisions. That's right. No intermolecular forces. The particles don't care where the other particles are. No volume. Volume matters, but the particle, the gas, takes up no volume. That's right. So here is your list. 1, 2, 3, 4, 5 criteria you must have. Well, sorry, 4. Ideal gases, though. We're talking about these point charges, little atoms. They're non-interacting, which means they don't care how many other molecules of gas are around. They go by the other molecules of gas without worrying that there's something else there. So we don't have to consider how one molecule of gas works with the other. Quick thing, where might that assumption break down? What kind of thing could I do to my gas that first one really starts not to apply anymore? What do you guys think? Temperature, that's just amount of energy. No, that might be one. Compress it, exactly. Remember, what we're saying is particles of gas go flying around in the cylinder and they don't even know that the other molecule of gas is there. As you start to compress it, you increase the concentration, right? Or at much, much, much higher pressure, they start bumping into other molecules of gas. That's where we start approaching really high concentrations and pressure, where it almost transitions to what state? If you compress a gas, what happens to the gas in terms of its state? Yeah, it becomes a liquid. So there's a threshold where ideal gas, weird system, liquid. It transitions down. Point particles, which means they don't have volume. And again, what we're saying is the gas atom, or the atom of whatever this gas is, it takes up a tiny amount of space relative to the container it's in. So we assume we don't have to, what that just means is, if I take n moles of gas, adding some n moles of gas does not substantially change the volume in this container. The container is just the volume that we measure macroscopically. It's just a small proportion of it all. And again, dilute systems at low as a gas at these kind of lower pressures definitely holds. Ceaseless random motion. This just means they are bouncing around off of everything, and by each time they bounce, that last point, there is perfectly translational kinetic energy. What we mean is a molecule of gas slams into the side of the container and it bounces off of it without ever losing energy to the container. So it's like the best super ball you've ever seen, right? It's going to be able to ricochet off of everything and it never ever slows down. The act of bouncing into things does not slow it down. So what does that mean? What's a property that we're kind of talking about slowing down particles and collisions? What physical property would you usually be measuring over this? Friction is one. No, that's true. Heat, kind of temperature. Bang, yes, kinetic energy. Heat, remember, think of it this way. Heat is the currency of energy. I have no money around. I'm a prof, I never have money. The heat is the currency. It is passed from unit to unit. That is the energy which is being passed over to different things. Temperature, though, is the average kinetic energy. So if a particle is flying along, it has energy. As it runs into something, we may transfer energy as heat. It pays a price, a toll for that collision, at which point it's moving slower. If a particle moves slower, if its energy or if its kinetic energy reduces, what we're really seeing is the temperature of that object will decrease. So this is a really important thing, and it's something we will challenge in the next couple weeks. Is heat the same as temperature? If I said this here, this water again is at so-called 25 or 24 degrees C. That's the temperature. The temperature is the average kinetic motions in the system. It is not heat. In fact, what we'll challenge is you can actually change the temperature of a system without changing the overall heat in that system. Also, I can add heat or take away heat without ever changing the temperature. Temperature is a measure of how fast things are moving. Heat is how much energy is contained or changed, exchanged as a result of some type of interaction, a collision. They're related, right? Generally, an object, if we put heat in, it will generally change temperature. But right now, think about something you've experienced in the world around you. And again, if this was summer, you definitely know this. Give me an example of a property or a process that you have done. You've added heat to something and it did not change the temperature. There's definitely something that you guys have all experienced some point of this, especially on a hot day in summer. Sweat? No, remember that's still, you're sweating and you're evaporating. There's things, well, actually no, you are right, that does count. I was thinking, yeah, phase changes, and that's where sweat counts, right? If you have liquid that is then turning to a gas, that's a phase change. Ice melting or water freezing, those are phase changes. If you undergo a phase change, what happens to the temperature? If we take a glass of, like a block of ice at minus 10 degrees, and I start to heat it up, it hits 0, and then as I continue to add energy to that block of ice, the temperature will not change, but solid ice becomes liquid water. The heat I am adding is now going into a phase change process. So we're still adding energy, we're adding currency, but it's not coming, the currency is not immediately changing over to heat, or sorry, currency is the heat. I'm adding energy. That heat currency does not immediately change temperature. We have to take all the solid ice and convert it to liquid water, and then we can keep changing temperature. So yeah, that's exactly the point to remember, and I want to put an emphasis on that now. Heat and temperature are related, but they are not synonymous, right? They are different pieces. Okay, so great, we've got this system. We have an ideal gas. The ideal gas, as long as it's in equilibrium, we can use the ideal gas law, PV equals nRT, to calculate this. Why does this matter? The reason why is because if I start at some equilibrium state, I can define it as some pressure, some volume, some N, some R, some T. If I then undergo a change, I add energy, I change the pressure, I change the volume. That change is the thing that's our thermodynamic process, but we can look at the final state from this. So if we're undergoing a change, what could you guys think of doing? How might I institute a change here? If it's a closed system, first of all, look at your equation. If this was a closed system, what value cannot change? PV equals nRT, it's closed. There's a value that immediately becomes constant. Well, R, yeah, R is constant always. Doesn't matter closed, open, anything. N. What is N? Remember, N is, number of moles. That's mass. If it is a closed system, I'm not changing the amount of moles. I'm not adding or subtracting mass from the system. So it's going to be energy. Energy will come in the form of either pressure, volume, or temperature. So we're going to move energy in and out of this system. Now this is where we're going to start off tomorrow, on Wednesday. We will start with some initial state. We assume it's at equilibrium. The ideal gas law applies. We are then going to add or subtract, move energy across this boundary, which means we're dealing with a closed system. N does not change. Because of that, we're going to have some final state where we have P2, V2, nR2. Now as long as, remember, R is a gas constant, N, if this is a closed system, will be constant. That means we're really dialing up and down this P, V, and T. Playing around with those three values will allow us to watch what happens inside the system. This is how we're going to be moving energy as heat in and out of this point. All right, so we'll kick off there. This is where we're going to stop for today. Happy to stick around and answer a few questions. I do have office hours today starting at 3:30 in the S block. Anyway, yeah, thanks so much, guys. We will pick up from here on Wednesday. Oop, sorry, bud. All right, does anybody have any questions?